Hello everyone. Today we will talk about planar graphs, one of the topics related to graph in discrete mathematics. Okay, so first we will see what actually a planar graph is. A graph here consisting of the set of vertices V and the set of edges E is planar if it can be drawn on a flat plane in which there is no edge intersection except the intersections in the vertices. So even though it looks like there is an intersection here, but if we draw it carefully, then we can use this kind of drawing or this kind of visualization for this graph. So this is a planar graph. Okay, so that's the meaning of planar graph. Yeah, this is an example of planar graph. Yeah, the previous example. K4 is a planar graph here because we can draw it in a flat plane without any intersection between the edges. But this one, K5, is not planar because no matter how we draw it, then there must be any intersection here. This is one of the drawing that minimize the intersection, but still there is an intersection here, yeah, just one intersection. A planar graph which can be drawn without edge intersection is called plane graph. Yeah, so actually a plane graph is a planar graph and it is drawn without edge intersection. Yeah, this is a planar graph. Yeah, actually this is a planar graph because we can draw it like this one. But specifically, yeah, the planar graph that has been drawn without edge intersection here is called plane graph. Yeah, this is plane graph and this is also a plane graph. And actually, both plane graphs represent the same graph, yeah, which is K4. Okay, so this is one of the application of planar graph. When we design an integrated circuit, then it is it is not allowed for us to have wires, yeah, that cross each other because it may lead to malfunction. So this is an example of the application of planar graph principle. There's no intersection between the edges. Yeah. In planar graph, we have the term region. Yeah, region. So region here is the area on a planar graph bounded by the edges. So if the planar graph should be drawn as a plane graph, yeah. So there's no intersection between the edges here. And if we have a plane graph here, yeah, planar graph which has been drawn as a plane graph, then the area on a planar graph here, bounded by the edges here is called the region. So in this case we have this region, yeah, a lot of things, a lot of regions here. 1, 2, 3, 4, 5, 6, and 7. A region is finite if the area is finite. So if we have edges, yeah, as the bound of the region, then the graph is finite. Yeah, so other than the yellow one here, yeah, the regions in this graph, in this planar graph, is finite regions, yeah, because the region is bounded by the edges here. But the yellow one, yeah, yellow one here, doesn't have outer boundary. Yeah? So yeah, it is bounded by the internal edges here, yeah, but outside actually there's no boundary. So the area here is infinite, and it is called an infinite region. Okay, this is an example of regions. Yeah? We have this planar graph, and from this we can have here 6 regions. This one, yeah, the first one, the second one, third one, fourth one, fifth one, and last one is the outermost region, which is an infinite region. Yeah? R1 to R5 are finite. Yeah? The only one that is infinite is R6 here, region number 6. Yeah. Okay, this is another example. How many regions does the planar graph G below have? Yeah? So we have here 1, yeah, 2, and then 3, and then 4, and then 5, and then 6. 6, and the 6th region is the infinite region. Yeah, so these are the regions here on graph G. Yeah, 1, 2, 3, 4, 5, and 6. Related to the number of vertices, the number of edges, and the number of regions on planar graph, we have this formula. It is called Eulerian formula. Yeah, so if we have V, E, and R are the number of vertices, the number of edges, and the number of regions, then for any connected planar graph, we have this equality. Yeah? So V minus E plus R equals to 2. Yeah? V minus E plus R equals to 2. This is an example. We have actually an edge here, yeah, between this vertex to this vertex. Let's separate R1 and R2. Yeah? So from this planar graph, yeah, the number of vertices is 11, and then the number of edges is 7, and we have 6. We have 6 regions. Yeah. To put it in the formula, then we have here the number of vertices, the number of edges, and the number of regions. So I don't think here the number of vertices should be 7. I think, yeah, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Yeah, so it should be 7 here, and then the number of edges is 11. Yeah. Yeah. So it is 7, and then it is 11, and we have 6 regions here. So this is the formula. Yeah, the number of vertices is 7, the number of edges is 11, and the number of regions is 6. Yeah, and 7 minus 11 plus 6 is 2. Yeah. These are examples how we use the formula, Eulerian formula, to find the number of vertices in this case. Yeah. So we have here these questions. How many vertices must be owned by each planar multigraph that has 10 edges and 9 regions, and then 12 regions and 28 edges? Yeah, so we use this formula. It is based on this formula. Yeah, so V here is E minus R plus 2, yeah? Because we have here V minus E plus R equals to 2. So V equals to E minus R plus 2. Yeah, yeah, just use this formula. So we will be able to determine the number of vertices. Yeah? So we have here 10 edges, then 9 regions. Yeah? So 10 minus 9 plus 2 is 3. So we have just 3 vertices here, yeah, for this the first planar multigraph. And then for the second one, 28 edges and then 12 regions. Yeah, so the number of vertices is 18. 18, yeah. If we have a planar graph, then we can draw the duality of the graph. So this is the method to draw the duality of the planar graph. We place new vertices in each region on graph G, then connect the new vertices to form a planar multigraph G. Yeah, so for example here we have this graph, yeah, graph G here. It has 1, 2, 3, 4, 5, yeah, five vertices, yeah, and 1, 2, 3, 4, 5, 6 edges. Yeah. If we place new vertices in a new vertex in each region, yeah, so we place here a new vertex in this region, and then we place here a new vertex in this region, and this one is also the same, yeah. So we have here three actually, yeah, three vertices. And then connect the new vertices to form we connect the new vertices to form a planar multigraph G. Yeah, so we connect this to that one, yeah. Cross the edge here, yeah. Cross the edge here. Yeah, so we have here from this to that, yeah, crossing the original edge, yeah, and then from this one to that one, cross the original edge, yeah, and from this one to that one, cross this one, from this one to that one, from this one to that one, and then from this one to itself, yeah. So we make a loop here actually. Yeah, so it will be, the result here is a planar multigraph G star. Yeah, that's the duality of graph G. Okay. We also have this inequality. Yeah? So if we have here simple connected planar graph, there are R regions, 3 vertices, and then E edges. Yeah? E is larger than 2. Yeah? Then we have this inequality, yeah, which is called Euler's inequality. So E is less than or equals to 3 times phi minus 6. Yeah. E is less than or equals to 3 times phi minus 6. This is not the this can be used, yeah, as the first indication, yeah, whether a simple graph is planar or not, but it is not the sufficient and this one, yeah? So it is not sufficient requirement, yeah, that planar graph, yeah, whether a simple graph is planar or not, yeah? So it is only a first indication, yeah. So if it is a planar graph, then it satisfies Euler's inequality. This is the first example. We have here phi is 4 and then E is 6 for K4, yeah, K4 here. The number of vertices is 4 and the number of edges is 6. And it is a planar graph. It is a planar graph. And it satisfies Euler's inequality because 6 here, E is less than or equals to 3 times phi minus 6. So 6 here, E is less than or equals to 3 times 4, yeah, the number of vertices, minus 6. But here on K5, we have the number of vertices 5 and the number of edges is 10. if K5 is a planar graph, then E is this one. Yeah? So E is 10, and then V is 5. Yeah? So 10 is less than or equals to 3 times 5 minus 6, yeah? Which is 9. So 10 is less than or equals to 9. And this is not correct. This is incorrect. It means that K5 is not planar. Yeah, so, but as I already mentioned before, the Euler's inequality is not a sufficient and necessary condition of a planar graph. We have here, for example, K33, a bipartite graph, yeah, with with 6 vertices here. The number of edges is 9. The number of vertices is 6. Yeah? So in this case, we have 9 is less than or equals to 3 times 6 minus 6. Yeah? 3 times 6 minus 6, which is 12. Yeah? So 9 is less than or equals to 12. Yeah? But so it satisfies the Euler inequality. Yeah? It satisfies the Euler inequality. But we know that K33 is not a planar graph. So again, the Euler's inequality can be used as the first indication, yeah, whether a graph is planar or not. But it is not a sufficient and necessary condition of a planar graph. So we have to be careful with this one. I think if it doesn't if it doesn't satisfy the Euler's inequality, then it is not a planar graph. But if it satisfies the Euler's inequality, then we have to check. We have to recheck whether it is a planar graph or not. So this is the one that is useful to determine whether a graph is planar or not. We can use a Kuratowski graph here. There are two types of Kuratowski graph. The first one is K5, yeah, complete graph with 5 edges, 5 vertices. And then the second one is K33, which is a bipartite graph. So we have these two types of Kuratowski graph. And this is an example of a graph that is isomorphic to the second Kuratowski graph. So if we can represent, or we can draw the K33 here as this graph. So this is isomorphic then. These two are isomorphic. These are the properties of Kuratowski graph. Both are regular graphs, yeah, as we saw here. K5 and K33 are regular graphs, and both are non-planar. Yeah? Both are non-planar graphs. We cannot draw, yeah, K5 and K33 without intersection of the edges. If we delete edges or vertices from Kuratowski graph, then we can have a planar graph. Yeah, so for example, for K5, yeah, we have two edges that have intersection, yeah, as we saw it in the previous slides. If we just delete one of the edge, yeah, then we will have a planar graph. Okay, the first Kuratowski graph is a non-planar graph with a minimum number of vertices, and then the second Kuratowski graph is a non-planar graph with a minimum number of edges. So those two have specific property, by itself. And this is the theorem that is proposed by Kuratowski to determine whether a graph is planar or not. Yeah? So this is a sufficient and necessary condition. A graph G is planar if and only if it doesn't contain an isomorphic subgraph with one of the Kuratowski graphs or homomorphic with one of the two. So if a graph doesn't contain an isomorphic subgraph with one of the Kuratowski graph or a subgraph which is homomorphic with one of the two, then it will be a planar graph. Yeah, maybe we can review the meaning of homomorphic graphs. Yeah, so if we have here G1, then G2 here is homomorphic, because we can get G2 from G1 by only reducing the number of vertices here. G3 is also homomorphic with G1 because we just add two vertices here. So these three graphs are homomorphic. This is an example how we use Kuratowski theorem to check whether a graph is planar or not. So we have here graph G. It is not planar because it contains the subgraph. The subgraph is this one, and it is the same as K33. So the subgraph here, sorry, this one, this is a subgraph of G, and exactly G1 here is the same as K33, bipartite graph. Since G contains a subgraph which is the same as K33, then G is not planar. So no matter how you draw it, then it's not possible for you to have a planar graph here. To have the graphs in which the edges are not intersection. This is another example. G is not planar because it contains subgraph which is homomorphic to K5. Here, by removing vertices having degree 2 from G1, then we get K5. So as you can see here, actually this one is homomorphic to K5. Since G contains subgraphs which is homomorphic to K5, then G is not planar. So this is the sufficient and necessary condition. Kuratowski graph is sufficient and necessary condition to determine whether the graph is planar or not. But yeah, still we have to check whether it contains the subgraph which is isomorphic or homomorphic to Kuratowski graphs. And it's not easy maybe for us to do that. Okay, that's it, I think. Planar graph. Thank you for watching, and I will see you again with another video related to the topic of discrete mathematics.